In this video, we'll take a look at logical operators. And to talk about anything that has to do with logic, we need to know what the basic unit of logic is. And that's this definition, which is called a statement. So a statement is defined to just be anything that is either true or false. And it could be a sentence, it could be a mathematical equation, it can't be things like opinions or things like that. So there are three common logical operators that we'll use, and there are more, but we're going to focus on these three. So we'll call these the common logical operators. So first of all, we need a couple of statements, and those are just the things that we'll use to build with these logical operators. So let's say first let P and Q be statements. So again, P and Q are both things that are either true or false. We don't know exactly what they are, but they're just placeholders, kind of like variables. So our logical operators are the following. We have one called OR, which is denoted by this V character. We have one called AND, which is denoted by the upside down V. And then we have one called negation, and that's represented by the tilde. So these behave kind of like how you would expect, with maybe the exception of OR. So let's just take a look at how these things behave. So first of all, let's just separate these two. So OR and AND are called binary operators. And that means that they take two things and they combine them together. That's where you get the binary from. And then negation is called unary. And it's called unary because it takes one thing, one statement, and it performs its logical operation on it. So let's first examine OR. So the OR operator we need to define, but since it's binary, it takes two statements. And so the way in which we define OR is how we want OR to behave, kind of based on how we use it in everyday life. So we're going to use this thing called a truth table. And a truth table is a table that contains all possible combinations of the statements that are inputs for the operator in question. And so in this case, if I want a table for the OR operator, P or Q, I want to be able to tell in every possible scenario for which P and Q are either true or false or some combination. I want to be able to tell if P or Q is true or false in those situations. And so since we have two variables, two statements that are inputs, we have these four possibilities. And I'll use 0 for false and 1 for true. So here, each row corresponds to one situation. So if we're examining P or Q, it could be the case that P is true and Q is true. Or it could be the case that P is true and Q is false, or P is false and Q is true, or they're both false. And those are the only four possibilities, and also that covers every potential possibility. So here's how we define P or Q. If they're both true, then P or Q is true. If at least one of them is true, then P or Q is true. And if they're both false, then P or Q is false. So notice, even though P or Q has two statements as inputs, it itself is treated as one statement. It's called a compound statement, whereas these are called atomic statements. They can't be broken apart into any smaller pieces. But P or Q is made of smaller pieces. Okay, so this is called a truth table, and this is how we define the OR operator. And again, keep in mind the OR operator is true if at least one of the two inputs is true. In these three situations is where that occurs. This is the only place where it's false. So we can also just tack on the AND operator, since we already have this table made up. So here's for the AND operator. The AND operator is true exactly when both inputs are true, P and Q. And so if at least one of them fails to be true, like in these three cases, then it's false. And that defines how the AND operator behaves. So this is telling us everything we need to know about the OR operator and the AND operator. So the negation operator is a little different because it acts only on one statement instead of two. That's why it's called a unary operator. So the negation operator has its own table, but it only has one input, and so our table only needs one variable, which means there are only two possibilities. Either that variable is true or that variable is false. And so not P, given that P is true, not P is going to be false. All it does is it switches the logical value, the parity. And if P is false, then not P is true. And that totally defines the negation operator. So these could be considered three separate truth tables, although these two are combined just so we don't take up too much space. So that's the OR operator, the AND operator, the negation operator. So let's do a little more complicated truth table. And let's say we want to find a truth table for the following logical statement, which is built out of two statements P and Q. It's the statement P or Q and not P or Q. So that's one statement. It's just a compound statement that's built of a lot of other ones. So I can make a truth table for this, but I want to do this step by step so that it doesn't get confusing. So first of all, I notice that there are, again, two inputs, P and Q. And so I have exactly four situations. Both are true, P is true, Q is false, P is false, Q is true, or both false. Okay, so I want to just gradually build up this entire statement by building up each part. And so the first thing I can build is this part right here, P or Q. And since the OR operator has been defined, then I know that P or Q is true in these three cases and false in the fourth. Now for this one I need not P or Q, and so I think I need this negation first. So I want to, again, gradually build up each statement. So not P, I have to look at this column because this represents P itself. So not P is false, false, true, true. And then once I have not P, I can make not P or Q. So this is true exactly when at least one of these two things, not P or Q, is true. So I'm looking at these two columns, not P, Q. And so if we follow this along and find out when is at least one of these true, here, not here, and those are both true. So now I have my two inputs. When I focus on this AND, the two inputs for this AND statement are these two rows, or sorry, these two columns. So now I can form my entire statement. Okay, so this is an AND statement, which means that this entire thing is true exactly when both of these inputs are true. So I need to follow along here and find out when both are true. So here, not there, here, and not there. So this is my truth table for this statement. I know exactly, given the situation for the inputs, if this entire statement is true, without having to go through every little detail. Okay, of course we had to go through the details to create the truth table, but in the future we can just look it up. So you can create any kind of truth table regardless of how complicated your logical statement is. So I want to go over quickly these two laws called De Morgan's laws. And these are two of the most important foundational building blocks for logical statements. And they're called laws because they're not assumed to be true. They can be shown to be true by truth tables, but we won't go through that in this video. So De Morgan's laws, they tell us how negation, we'll say, distributes over the OR operator and the AND operator. And there's one law for each one. There's De Morgan's law 1, De Morgan's law 2. So distribute means just the same as how we distribute like addition over multiplication or multiplication over addition. So what we're going to do is take the negation of P or Q, the negation of the statement P or Q. And De Morgan's laws says that this statement, the negation of P or Q, is equivalent to, which is denoted by this double two-sided arrow, not P and not Q. So what De Morgan's law says here is that in order to distribute the negation over P or Q, each of the statements P and Q gets negated, and we flip the sign. So we flip the operator from OR to AND. And then De Morgan's law, the second part, shows how negation distributes over an AND operator. And it behaves just like the first law, except we have not P or not Q. So these are De Morgan's laws. If you wanted to, you could get truth tables for, say, the left side of the first one and the right side of the first one. You could build it just like you did here, and you would see that the columns of the truth tables matched exactly. So that would be a short proof for De Morgan's laws. But mostly for us, De Morgan's laws are useful if we want to distribute. So not back to the truth tables, but just the actual usage of the logical operators. And also De Morgan's laws are important, very useful in logic. And that's it for this video.